So here we are just trying to explain this to you again in a very simple way, that if it is a material, right? For example, this piece, this column, and we are applying some load, right? Here it is fixed at the top. We will pull it from here. We will apply a tensile load, pull it. So just to explain, we take a very small portion here and enlarge it and show atoms or molecules of the metal or whatever inside. So when we apply the load, the force F, then some deformation delta is there. Right? And what happens, that this square piece becomes rectangular, right? And the bonds between the atoms or molecules, they stretch. They do not break, they stretch. So the shape changes. But when you remove the force, all this deformation is gone. This piece goes back to exactly a square shape, and all the atoms and molecules that were stretched go back to their original locations, right? So this was the condition. After a small load, this is the condition. After unloading, this is the condition. So now if you do this process on a graph, force on one side, deformation on the other side, then this type of a small load deformation is a straight line, linear elastic, or it is a curved line, non-linear elastic. Now you tell me, what is the difference between the brown line and the green line? First, let us see what we are saying here. Elastic means reversible. In terms of deformation, right? Has the material deformed? Reversible means no, it can go back. So that is what we are doing in these graphs, right? This upward arrow means we are deforming, isn't it? We are applying more load and it is more deforming more. So this upward arrow goes there. But when we remove the load, it goes back to zero. On the green one, we are deforming. But when you remove the load, it goes back to zero, right? So what is the difference between the brown and the green one? Both are elastic. Elastic means what? Elastic does not mean whether it is a straight line or it is curved. Elastic means that when you remove the load, the deformation goes back to zero. Do you understand? So this is very important. The deformation can happen in a linear manner on the graph. It can happen on a non-linear manner in the graph. But if at the end of unloading, the deformation is back to zero, then it is elastic in both the cases. Now, you will see later on that metals and metal alloys behave in this manner. When the deformation is elastic, then the graph is linear. But some types of plastics and polymers, especially rubbers, they are elastic. As soon as you remove the load, they go back to the original shape and size, but the graph is a non-linear graph, right? So for some polymers like rubbers, the graph of force and deformation is non-linear. It is not a straight line, but it does not mean that it is not elastic. Of course, if the load is too high, then it will become plastic. That is something else. So now we go to plastic deformation. We start with the same thing, right? We have the same bar, the same small piece, but this time we are saying a small load, but it is larger than the previous one. So the deformation delta is much larger. And if you see, it has become a rectangle, but a thinner and a longer rectangle. And now the way we are showing you, bonds have stretched and the planes have sheared. This plane has sheared and gone out. It was only until here. This plane has sheared and gone out. So bonds have stretched and some shearing across the planes has happened. So now when you remove the load, unload it, it does not go back to the initial situation. It goes back a little. You see, it is not exactly the same size. It goes back a little, but the planes still remain sheared. The bonds that were stretched have gone back to some of the original sizes, but the shearing across the planes is still there. So now it is not this long rectangle. This is a smaller rectangle, but it has not gone back to the square, right? So therefore this time when we apply the load, the deformation, some portion of it is elastic which will return back, and some portion of it is plastic which will be permanently there. So when you completely unload it, some permanent deformation is there. This is the delta plastic. And you see, this was the total delta. When you applied the load, this much was the total deformation. Some of it has gone back, right? Some of it has gone back. The portion that has gone back was the elastic portion, delta elastic, that has gone back, and the delta plastic is there. So plastic means permanent, right? Reversible, no. Some portion of it is still reversible, some portion, but some permanent deformation is there. So in terms of deformation, plastic here means permanent deformation. Now if you look at the graph, then you can see that the initial portion of the graph is still linear, but then some curve starts to happen. So if I apply more load initially, if it was a metal, I'm not talking of rubbers, if it was a metal, all the linear, but once load is more than here, then the curve is non-linear, and now it cannot go back. So if I have loaded until here, then this is the deformation, right? Until here, this is the deformation. But if I remove the load, what happens? So you know from your earlier courses that the unloading diagram, you make a line from here at the point where you stopped the load, make a line which is parallel to the initial straight line, and the unloading will happen on this line. This is the loading line. We are increasing the load. We reach to this maximum load that we wanted to apply. Now we are unloading it. So when we unload, then we end here. So now some permanent, it has not ended here. So this much of permanent deformation is there, delta plastic. But at the time of loading, it was here. So from here till here is the elastic portion, delta elastic, which has returned. So you see, you know this, but I am repeating it so slowly so that it is very clear that what is elastic deformation and what is plastic deformation, and why is it important, we will see later on, right? Elastic and plastic deformation. Based on this, now we can start defining the engineering stress and the engineering strain. Now I have requested you many times that if you really want to understand a lecture, then please do not read anything. Only the heading, engineering stress and strain. And below that, don't read anything. I will ask you a few questions, you will respond, you will pause my slide, and so on. And that way you will really understand. Otherwise, if you start reading and your mind is not really sharply alive, then you will not be doing a very good job of understanding.